Hi, my name is Nikiforos.
Hi, my name is Caroline Kucher.
Hi, my name is Matthew Smith, and our project is a pure sinusoidal wave inverter with a single to three-phase power converter. Our advisor is Mike Otis. The problem is that some devices require a nice pure sine wave, however most common low-budget DC to AC inverters are only capable of producing modified square waves. While this might work for certain applications, it will not work for some very precise devices. Another problem this design addresses is that most of the time when you see three-phase voltages, the voltages are extremely high and therefore dangerous. This makes it more difficult for students to experiment with three-phase voltages and to learn how they work. To address these problems, we have designed a product that will generate a variable frequency AC waveform from a low voltage DC source, then split the single phase AC voltage into 3 different phases and filter out all the unwanted harmonics to keep the waveforms as close to pure as possible. This project is significant as it will serve as a great way to learn about three-phase power safely and will also be able to produce a near perfect sine wave for a very reasonable cost.
The engineering constraints that drive this project include an accuracy within 10%. The phase splitter must output 3 sine waves of equal magnitudes and with phase angles 120 degrees apart in order for it to be a balanced system. The used parts must be readily available from major retailers, and the final product must cost below the $200 budget. The applied engineering principles and theory include circuit analysis and electronics for the phase splitting, filtering, and power amplification, and microcontroller programming to convert the DC input into a variable frequency AC output, and for the three-phase data acquisition. This prototype serves as the foundation of the overall project. It splits a single phase input into a variable three-phase output. The amplitudes can be any value between 0 and 15 volts, and the output phase angles can be changed to any value between 0 and 180 degrees per phase. This prototype will be used to test design additions such as the variable frequency AC input, filters, power amplifiers, and data acquisition.
Due to resource and time constraints, we needed to prioritize prototyping the single-phase to three-phase converter, since this is the core of our project. In doing so, we confirmed that the core of our project worked in accordance with our theory and simulations. The first iteration of our design significantly reduced the number of parts necessary for the single-phase to three-phase conversion to work. I was able to reduce the number of operational amplifiers from 5, shown here, down to 1, shown here on the right, as well as solve the problem where the amplitude of each output phase was different, causing a situation where each output phase would have to be tuned manually so that they were equal. The iteration shown here on the right, each output phase will now automatically be exactly what the input is. Which is convenient, and so there's no more manual tuning, and reduces the number of op amps needed from 5 down to just 1. The plan moving forward is as follows. Over winter break, we will prototype and test the DC to variable frequency single-phase AC, the AC power filtering and amplification, the three-phase data acquisition and control system. That way, by the time the spring semester begins, we will have each individual part working so that we can begin assembling the individual prototypes to form the complete system. From there, we will use the remaining spring semester to refine and finalize the project. Welcome to the video demonstration of our project. Here is the input to the single-phase to three-phase converter from this function generator, 60 Hertz sine wave with an amplitude of 2 volts. Here's the constructed prototype on our breadboard. These 2 potentiometers control the output phase angles. Here's the my oscilloscope with it measuring the 3 phases. So the yellow line is the input, the let's see, pink line is phase 2 and the blue line is phase 3. So the measurement of phase angle 1, 2 is 120 degrees. Phase measurement of 1 to 3 is 240 or minus 120. And then the phase angle measurement of 2 to 3 is also 120 degrees. The amplitudes are all the same. Peak to peak voltage 3.96. So basically, an amplitude of 2 volts